Okay, now we're up to parametric equations. Okay, so in high school, all the way up until now, we've been learning Cartesian equations. So, we've been doing the classic y equals x squared, y equals x cubed, even modulus functions, hyperbolas. But you're in Big Boy Extension 2 now, so it's time to learn about parametric equations. In 3D, it's really hard to actually define lines easily. In 2D, it's really simple, right? We just have this. But in 3D, it's definitely far more complex to do it. So vector equations is actually a really simple way, because vectors are actually just lines in a 3D space. So it's actually a lot easier to make a vector equation first and then make a Cartesian equation from the vector equation, if you'd like to make a Cartesian equation. Yep. So in 3D, this can be very impractical sometimes, and it can be very hard to describe curves using x, y, and z. So we can use vector equations to deal with this, where we use parameters, not unlike the ones we've seen before. Okay, so in extension 2, we're interested in vector equations of lines, and if we have time, I'll also extend this to planes. Okay, so the parametric equation of a line. The equation of a line is as follows. So the line r tilde is defined by a tilde plus lambda b tilde. So this is basically a starting point. And this is our movement vector. Now, why is it called the movement vector and why is it called the starting point? Well, I want you to imagine. Also, another tip here is that when you actually draw vectors, just to help you understand your own working out or help you understand a question, it's honestly probably better if you just draw them as 2D vectors, right? So you have a vector A, right? And you want to define a line, right? In fact, this could just be a position vector. So let's just actually define A as OA. And then we'll have A here. So we get to A. Yeah? And then our movement vector B can really be any length of B. So it can be 0, which would be just land back at A. Or it could be 1,000 and we'd be going, I don't know, all the way over here. Or we can go negative 1,000 and all the way over here. Sorry, it's not straight. It should be straight. So now you're starting to get it, right? By using this lambda, by using this arbitrary lambda which exists in real, we're able to manipulate vectors to create a line equation. So that's the whole gist of vector parametric equations. Okay. Find a parametric vector form for the line through the point 0, 2, 1 and parallel to the vector v equals 2, 4, 1. Okay, so this question is asking us, I want a line that goes through 0, 2, 1 and is moving along with the vector v equals 2, 4, 1. Okay, just from how I've rewritten this equation, if we go back, I explained the two components of the vector equation as the starting point and the movement vector. Now, what's our starting point? Well, starting point is obviously 0, 2, 1. So let's just define the line as r, as our definition did. So r equals 0, 2, 1, which is the position vector of the point that we want to start at, plus lambda, where lambda is some real number, lambda, and we want to be moving along the vector v. So 2, 4, 1. So that's actually it. I'll quickly introduce a quick side note. We know our vectors are represented by the x, y, and z components. So if we actually add on the lambda into our function, we get 0, 2, 1 plus 2 lambda, 4 lambda, lambda. And then if we actually add these, we get 2 lambda, 2 plus 4 lambda, 1 plus lambda. So that means our components are x equals 2 lambda, y equals 2 plus 4 lambda, z equals 1 plus lambda. Yeah? So this is how we actually get the components defined parametrically. And this will be important later on when we want to find the Cartesian equation. Okay. The points A and B have position vectors A tilde equals 1, 0, 1 and B tilde equals 3, 4, 7. Find the parametric vector equation of the line passing through A and B. All right. Okay. So essentially, we want to define a line such that it passes through like this. Yeah. Just gonna make this shorter so I have some space. Okay. Which point is going to be our starting point? Okay, I can't get user responses from you. So I guess we could, let's first define these. So A, B. So we could have this point. We could start from this point, this point, this point, this point. And my whole point is that you could really choose an infinitely amount of different, we could choose an infinite amount of points that could be our starting point. But realistically, what's going to be our most easy point to use? It's going to be A or B. And it shouldn't matter because if we have, if we have the origin here, that's our position vector to O and A, sorry, O to A and O to B. If we have the movement vector, if we choose O to A, it'll be able to reach B. And if we choose O to B, it'll be able to reach A. So either one you choose doesn't matter. Let's just choose A. So R equals 1, 0, 1. Okay. Now we need to find the movement vector. How do you think we could find it? Well, we need to find, we've been given that the line intercepts through B and A. So the vector between B and A, that segment, actually represents how much our line is moving. So our movement vector is defined by B minus A, but can it also be defined by A minus B? Yes, because again, when we have a parametric equation, the lambda can be negative, so it doesn't really matter which way you choose, but let's just go through B minus A. So again, if you're doing this question by yourself and you come back to this equation that I've already created and you go, oh my god, this is so different to yours, I used B instead of A, and then I used A minus B, don't freak out, you're still correct, and you'll still get the question correct. In fact, if you wanted to, you could, in fact, I'll show you something real quick after I solve. So let's do B minus A. 2, 4, 6. And this will equal lambda 2, 4, 6. Now, let's try and find another starting point for fun. So what happens when lambda equals 1? Well, that happens. And then we get the point 3, 4, 7. Now, if we replace our starting point, with 3, 4, 7, is this still valid? I'm going to give like 10 seconds for people to respond. Hopefully people do respond. Is this still valid? Yes or no? It is valid. because I can still reach what I want if I do -1, right? So my whole point is that there are literally infinitely amount of ways to define a parametric equation. In fact, if I times this movement vector by another scalar, it would still be valid. If I times this by 1,000, it would still be valid, because all lambda would have to do would be some fraction to get to these other points, right? So yeah, if you understand that, you will basically understand vector parametric equations. Okay, and there's a slide talking about what I said. So hopefully I've already repeated this 100 times before reaching the slide, but don't worry if you have different parametric representations to the answers or other people. There are infinite ways to represent the same line. Okay. Does the point 32, -6, and 23 lie on the line x, y, z equals -3, 1, 2 plus lambda, 5, -1, 3, and does 0, 0, 0? Okay. I want you guys to imagine vector parametric equations as a contract between you and the line. Okay? Stick with me. So, a vector parametric equation is like this. Okay? And you as a user might come with a point like 6, 7, 4. And you go, excuse me, the line, is this point in the line? And then the line will go, well, my x values are defined by -3 plus 5 lambda, where lambda is some real number. My y values are represented by 1 minus lambda, where lambda is some real number. And my z are represented by 2 plus 3 lambda. So basically, the line is restricting where x, y, and z can be placed, because they're all the same value of lambda, right? So how do you think you could solve this question? I'll give maybe 10 seconds just for any live chat responses. Okay, the way to solve it is to, as we've done multiple times throughout our high school career, which is substitute. So to check if a point lies on the line, we check if the contract stays true. So we let x equal 32. Just making sure I'm not passing into my webcam. 35 equals 5 lambda, lambda equals 7, right? Now that we have this lambda value, all I have to do is sub it back in and check if we are, keeping it in contract. So our y value would be 1 minus 7, which is -6, which is in contract. And then z equals 2 plus 3 times 7, which equals 23, which is in contract. Therefore, this passes the contract. Therefore, on the line. Okay. Now, does 000? Same way, we can do what we just previously did. And we just sub in the points again. So 0 equals -3 plus 5 lambda. 5 lambda equals 3. Lambda equals 3 on 5. Yeah. And then y should equal 1 minus 3 on 5. But this equals 2 on 5. So 0 is always going to, the x value is always going to suit the contract, because that's basically our defining terms of the contract. But then y does not meet the contract. Therefore, this does not lie on the line, and this does lie on the line. If you have any questions about this solution, just leave it down in the question below, in the live chat. Okay, which pair of line segments intersect at exactly 1 point? Well, let's think about this intuitively first. Yeah. How many different ways can a line intersect? Okay, so there's case 1. In fact, I'll give you guys a few seconds to think about this. So case 1 is no intersections. Case 2 is 1 intersection. And case 3 is infinite intersections. Right? So what is a no intersection going to look like? Well, it's going to look like something like this. Sorry, I'm just moving my laptop so you see my monitor. Okay. 1 intersection will look something like this. And then infinite amount of intersections will just be when the line is the same. Yeah? Okay. Now, I'm going to quickly show you how to do this question effectively, because I don't want you guys to see this in a multiple choice question and then spend like 20 minutes on it, right? Okay. What I'm looking for, I'll take you through what I'm looking through. The first thing I'm looking for is where the starting points are the same. So D, the starting points are the same. And I'm going, okay, that's a good way to start. If the starting points are the same and the movement vectors are different, so if it's like that, it's gonna have 1 intersection, yeah? But are the movement vectors different? What do you guys think? Are they different? I guess, but not really. Why not really? Because if I did this, right? Let's say I factored out the 2 from the 2, 4. This gets swallowed by the lambda, right? So in reality, these 2 movement vectors are moving the same direction. So it's definitely not D, because since these 2 lines are the same line, they're going to have infinitely many intersections. Yeah? Let's check this one. Okay. These 2 have the same movement vector, but do not have the same starting point. That's peculiar. Okay. So that means these are parallel lines. Yeah? Let's factorize out. And actually, let's just make it the same. So what I've done here is I've factored -3 out of this movement vector. And that's valid. Actually, that is not valid. Wait. No, that is valid. Because lambda will just eat that, and then, yeah. Is this going to have exactly 1 intersection? Well, can we create... We can't create V with U, so no, these won't be, these will not be intersecting. In fact, let's prove this a bit more formally. Do I have a working out page? No. Let's prove this a bit more formally. So x equals 1 minus lambda, y equals 2 plus 3 lambda. So what I forgot to do, which I apologize for, is look at the domain first. Yeah. So the domain is restricting my lambda's values. Okay. So x equals 1 minus lambda plus 5 plus 3 lambda, which is just going to equal 5 plus 3 lambda equals 1 minus lambda, and then 6 equals 2 lambda, and lambda equals 3. Already we've got problems. Already we've got quite big problems. Actually, sorry, it's going to be 4 equals 2 lambda. Sorry. Wow, I have made so many silly mistakes. I'm so sorry. 4 equals -4 lambda. Lambda equals -1. Is that valid? No, it is not valid. So let's move on from this question. So B is not correct. Let's check C. These 2 have different starting points and different movement vectors, so this might actually be a good contender. So x equals 2 lambda, y equals 2 minus 2 lambda, x equals lambda, y equals 3 minus 3 lambda. And then lambda is going to equal 0 here because lambda equals 2 lambda, lambda equals 0. This is equating the x-axis, the x components. And when lambda equals 0 in the y components, this one equals 2 and this one equals 3. So these actually don't have any intersections. And by elimination, it's A. But let's check, just in case I've been a little bit of a dummy. Okay, so x equals 1 minus lambda, y equals 2 plus 3 lambda, x equals 3 plus lambda, y equals 1 plus lambda, 3 plus lambda equals 1 minus lambda, 2 equals negative 2 lambda, lambda equals 1 minus lambda, okay, sure, lambda equals negative 1, okay, and then we've got 3, 3 plus lambda equals 1 minus lambda, 2 plus 3 lambda equals 1 plus 1 lambda, 2, what am I doing wrong here? Okay. Let us start from the beginning. I'm going to do it formally now. 1 minus lambda. X component is going to be 1 minus lambda. So immediately this one isn't correct either. Two lambda. Lambda equals 0 here, and this one shouldn't be correct either. One minus lambda equals 5 plus 3 lambda. 3 lambda equals, 4 lambda equals negative 4, negative 1. And yeah, this isn't right either. My apologies. Yes. Okay. It is D. Now, the only reason for this is because of this domain. So my apologies for the earlier mistake. This is actually a good learning lesson for us. It's really important to read the full scope of the question. So the reason I can't actually factor out 2, 4 is because of this restriction. And because of this restriction, there's only one point this intersects, which is at 3, 1. Yeah. Okay. X equals 3, 1. And that means 3 plus lambda equals 3 plus 2 lambda. Lambda equals 0. And then when we substitute 0 into both of these y's, that just becomes 1 and 1. So yeah. So it's D. Okay. If I have made a mistake, please please feel free to call me out in the live chat. At the end of this recording, I'm going to quickly go through that question again, make sure I've gotten everything right. And if by the time of this live stream, I've made some silly mistake, I'll make sure you guys know, okay? Okay, which of the following vectors is equal to AB plus CQ? Okay, so we've got AB here. And we've got CQ going through this vector here, right? So this does not mean the vector is that. No. This means the vector looks more like this. So let's move CQ over here, and then the vector will look something like that. It's going to be AR, yeah? So is it equal to AQ? No, because that's the example I just talked about. It's definitely not that. Is it equal to CP? Immediately, yes. Immediately, this is the answer. But I'll go through the other examples and explain why they're wrong first. But this movement is going... Let's remove everything real quick. So CP is just a diagonal. So remember, vectors aren't fixed in place. Vectors only talk about magnitude and direction. So it doesn't actually matter where they are as long as they can keep their magnitude and direction. So AB plus CQ looks something like this. So it's going down, it's going right by one and then across a diagonal. And CP is going right by one and up a diagonal. So it's the same thing as AR. Sorry, it's the same thing as AB plus CQ. Why is PB wrong? Let's look at PB. PB is again the same as AQ. It's way too long. And RA is negative AB plus CQ because RA is that way. Okay, any questions, please feel free to ask. Okay. Consider the two vectors u equals negative 2i minus j plus 3k and v equals pi plus j plus 2k. For what values of p are u minus v and u plus v perpendicular? Okay, well, u equals -2, -1, 3, v equals p1, 2. Now, u minus v is going to be -2 minus p, -2 and 1. U plus v is going to be -2 plus p, 0 and 5. Okay, and they are perpendicular, if you remember, when the dot product of the two vectors are equal to 0. So, u minus v, u plus v equals -2 minus p, -2, 1, dot -2 plus p, 0, 5, which is equal to 4 minus p squared plus, how I got 4 minus p squared is actually, these are just perfect squares, plus 0 plus 5, which equals to 9 minus p squared, which equals 0, which equals p squared equals 9, which equals p plus p equals plus or minus 3. Cool. Again, any questions about this question, please leave it down in the live chat.